My name is Rob Galanakis.
My name is Natalie Edson.
We're the founder and senior software engineer at WebhookDB. Today we have something fun to present, at least we hope it's fun, definitely a bit different than many of the other talks. We're going to build a complete and comprehensive async API specification without writing a single line of it ourselves. So let's set the stage. There are two things you should know. First, about our company. It's just the two of us right now. We'll talk about our product, WebhookDB, in a minute, but we also run a software consultancy, Lithic Technology. We're juggling clients and customers and support and life. There's always quite a lot going on.
The second thing that you should know is that we're pretty lazy. Lazy, of course, meaning that we want to spend time doing things that we enjoy doing and then avoid spending time doing things that we don't enjoy doing. I'm a published poet. You can see here in these pictures me reading at a poetry reading. Rob is the primary parent to his two children. You can see Rob here being very silly. Thankfully, we also enjoy programming, but when we do program, we like to really let our creativity flow. We're not specification people.
On top of that, I'll come out and say I'm not a huge fan of code generators. I'm also skeptical of any technical documentation artifacts I run across in version control, and my eyes run right over this sort of specification language that reads like someone's lecturing a misbehaving child. There's no question, though, that specifications are absolutely vital to the world of programming, and I'm very glad there are people that enjoy building them. Just because I do not is not a criticism of specifications as a pursuit, but it does make us very strange speakers at a conference designed around a specification. Like, how did we get involved with AsyncAPI in the first place? To answer that, we need to tell you a little bit about WebhookDB, our software product. I'll keep this short since this is not a sales pitch. WebhookDB is a self-hosted or fully managed data reservoir that instantly synchronizes, schematizes, and normalizes data from third and first-party APIs and can be queried using SQL. Or put another way, we take data from APIs, jam it into a Postgres database so it's normalized and structured, and then you query that database.
The biggest challenge of an integration product like this is the sheer variety of programmer expression that exists. Every time we start a new integration, we have to be prepared for anything. No documentation, examples, or staging environments are ever complete, and many APIs lack them entirely. This is a particular problem for WebhookDB because we also support what we call the API 99%, which is the long tail of companies that offer APIs as an additional thing rather than their main product. Integrating your Stripes and your Shopifys isn't so difficult, but most APIs aren't up to those standards. This, for example, is part of an actual payload from an API we support. There's a lot going on here, and it's trickier than it seems at first look. Like, you can't really tell what the start date and end date refer to in terms of AM and PM. You can only know for sure by seeing more data.
So every time we have to integrate an API, we'd have to carefully go over documentation and examples, implement based on that, hope everything's correct, and tell me if you've heard this one before, continually find out all the ways the production API differs from what's documented. But we're lazy and a small company, and I don't like fixing production issues at my kids' soccer practice, and we like building silly but sometimes useful stuff. So we stepped back and said, is there a better way? Yes, there is. Well, maybe there is. What we realized is that instead of integrating an API and then testing it live, we could capture a bunch of data from production and use that to drive the integration. From there, we realized it's actually quite difficult to understand an API by looking at 1,000 different individual API requests. We needed a way to classify them. This is what led us to AsyncAPI. Instead of using a specification to drive and control the development of a service, we could use it to classify and describe a service that already exists. That is, we could feed individual requests into a program that generated an async API spec even before we started writing a real integration. And then we decided we could use the specification to create fixtured events and publish them against WebhookDB as a way to regression test every single one of our integrations. It was a real aha moment that instead of using the spec to circumscribe development, we could use it to explore unfamiliar systems and navigate how we integrate with them. This could bridge the gap between the highly structured procedural world of specifications and the freer flowing, more artisanal style of programming that we like to do. So we set out to build a tool that could accomplish this for us.
To do this, we depend on cutting-edge techniques across the disciplines of machine learning, genetic programming, multivariate statistics, and formal proof modeling. Just kidding, it's a lot of if statements. The tool we built is called Mox Populi, or MoxPop for short. When we think about authoring specifications, there's normally a central group that makes decisions, and then it is up to other devs to ensure that their services conform. MoxPop flips that on its head. The implementation is what drives the specification. MoxPop generates specs for how your service integrates with an external service. This perspective has been important for us while working on WebhookDB because we're working primarily with third-party APIs that don't have formal specs and cannot be modified. Here's how all this works conceptually. Events are published by external services on the left to your service in the center. When you use Mox Populi to build a spec for your service, these events end up describing subscription messages. As events from the external service are handled by your service, you sample and record them at full fidelity. Those recorded events get fed into MoxPop, which generates AsyncAPI specifications and then incrementally improves them using newly recorded events. Finally, you can use those specs to generate fixtures that you can publish back to your service as part of integration tests, or to generate data for unit or fuzz testing.
That was a lot, so let's break it down into 4 steps. The first step is recording events. Then we use the recorded events to generate JSON schema for message payloads. Then we use the recorded events to generate the rest of the AsyncAPI spec. And finally, we turn generated specifications into fixtured events and publish them to our service. This first step is the most straightforward. Capture full fidelity events in whatever format they're being published. For example, if these are HTTP events, you'll need to capture the method, URL, headers, and body, even if you think you only care about the body. If you've captured enough information so that you can replay the event, you did it right. Also, you'll probably want to sample the events you capture. There's no reason you'll need to run MoxPop for each event.
Step 2. Generate JSON schema for message payloads. This is where MoxPop enters the picture and things start to get interesting. In this step, we're not actually focused on AsyncAPI. We're just focused on JSON schema. We take a JSON object and generate the JSON schema that describes it. Now, without using MoxPop, here's the JSON schema that we would expect. On the left here, you can see we have 2 different integers. From our experience as developers, we know that these integers probably mean very different things, but in the schema that gets generated, they're both described in the same way. So the schema is very accurate, but it's not very precise. To generate schemas that we can use to generate fixtures, we need to be both precise and accurate. These targets from left to right show low precision and low accuracy, like a JSON schema with just a type, which is what we just saw. It doesn't provide much detail about anything. Then we have high precision and low accuracy, like if we generate constraints that are wrong. Low precision but high accuracy is like if we use the format property. Knowing a string is in a date format is useful, but it doesn't tell us anything about the actual date being represented. And finally, we have high precision and high accuracy, whatever that means. We need to achieve high precision and high accuracy. That's what MoxPop schema generation is all about.
This is where we start to get creative. We can use AsyncAPI extension properties to provide a new layer of precision to the data we've seen. Using MoxPop, this is the JSON schema we'd end up with for the previous example. You can see here that we have an extremely high level of precision, but probably too high. We've made a lot of assumptions. These assumptions are likely to drive down accuracy. We assume x will always be a 32-bit integer, and that z will be an integer and a timestamp. We can't know these things for sure, though. It's very likely we're wrong about one or all of the assumptions we've made. So, in order to improve accuracy, we can generate schemas for many payloads and merge them together. This resulting schema has a decreased precision but increased accuracy. For example, what we thought was an integer may actually be a floating point number, or could be a string in some cases. We keep fitting the schema to the data we see. The fitting process is commutative, so we can keep doing this incrementally as we record new events. The resulting schema will always be accurate for all events ever processed.
However, there are a few cases where we can't be precise at the beginning. For example, if we get a random string of ASCII letters and numbers, we can't tell what it is right away. It might be an identifier or maybe a free-form text entry. In these cases, MoxPop will store and accumulate the values we observe in each payload, as we see on the left here. Eventually, after we've sampled enough data, we can make a decision about the schema. For example, if every value we've seen has the same length, and they'll seem like identifiers, we can assume it's an ID field. We do the same thing for enums. At some point, we've seen enough samples and seen few enough distinct enum-like values that we can assume the field is an enum. These enum values get put into the enum JSON schema property.
Recording information in the xSeenValues property is tricky because there may be sensitive values we don't want to include. Sometimes access tokens or IDs come through in an event. Whenever we get a string value that looks like gibberish, we generate a new string value of the same size and use that so that we never write out IDs, tokens, or anything else sensitive.
One last thing MoxPop does is record copies of payloads into the examples field. This allows you to see actual event payloads in the spec. We try to be clever about when we collect them, like when a property format changes. Being selective about examples bridges the gap between reviewing the API in the abstract only through the specification and reviewing it only through live events. You get the best of both worlds. The API is condensed into a spec, and every example shows you some unexpected change vector.
So putting it all together, here are some of the formats and properties MoxPop handles. You can see full examples in the GitHub repo. The version here uses a superset of AsyncAPI and JSON schema formats, plus some formats describing data we've seen in the wild, like numerical strings and integer timestamps. These additional formats, coupled with the constraints in the seen values, give us an accurate and precise description of the data we see from an API.
So the previous step was all about generating JSON schema for payloads. We're going to take the same idea and apply it to the rest of the AsyncAPI specification. We can actually generate most of the spec from the full fidelity events we record. We can't handle sections like info that require out-of-band information, but we can do quite a lot. I'll warn you here that the examples in this section are HTTP specific. Because WebhookDB is focused on webhooks, most of our usage is HTTP based. All of these examples should work for other protocols, but we wanted to warn you as we'll be using HTTP-specific terms ahead. We can take each component of the HTTP event and figure out what parts of the spec the component applies to. Path, method, and body map directly to channels, channel bindings, and message payload, but request headers are more interesting. The HTTP request headers map to multiple parts of the spec. We categorize headers into special, protocol, and application headers.
Special headers are those with a special purpose. For example, host and accept can be used in the server object, describing the server URL and protocol versions. The content type header sets the message content type, and we can figure out the message correlation ID by guessing which header, if any, looks like it's the correlation ID. For protocol headers, we keep a list based on HTTP standards. Any protocol headers are set on the message HTTP bindings headers, as in this example. We include the actual header value in the JSON schema, so the spec is easier to understand. Protocol headers, as you may guess, can't really be fixtured since the value is meaningful for the protocol. In these cases, we end up ignoring them or using the X last value verbatim.
Finally, anything we don't identify as a protocol or special header, we treat as an application header. For application headers, we use the standard MoxPop deriving and fitting, so they get as much fidelity as the message payloads. When you put this all together, we can take some recorded events and generate a totally usable and valid async API specification. You can see the full example in the GitHub repo, which is linked to at the end of the talk.
All right, we're finally at the reason we built Mox Populi in the first place, which is to use the generated async API specs to fixture and publish a huge number of events against the service. There are two types of fixturing going on, and here's the first one. MoxPop can create fixtured objects for the JSON schema we saw generate previously. It uses all the extension properties to make sure the fixtured value looks pretty close to real. There's obviously a lot of fake data here, but from a technical standpoint, this looks legit and probably exercises the same code and database paths that real data would. The detail in the fixtures comes mostly from the number of custom formats, which we saw earlier, but also the extension property fields act as constraints that narrow down the fixtured values. For example, if you have a created field that's an integer timestamp, all the fixtured values would be between the minimum and maximum that's been seen in any recorded event. You won't get created values from 20 years ago or 20 years in the future.
Finally, here's what happens when you run a regression test against MoxPop Vox and your service's async API spec. It publishes the configured number of events against a server. We use this fixturing to both load test and integration test our backend. What you see here is the request and response dump of a fixtured HTTP request sent to the server and the actual server response. Again, you can see we're getting pretty nice fixtured data, and the server accepted it happily. So what have we learned building Mox Populi? 3 big lessons.
The first is that AsyncAPI truly can describe any kind of API. This was our first time using it, and we were super impressed. I've done pretty extensive work with OpenAPI, and AsyncAPI has some subtle and significant improvements. I think all of them are great. I know I'm preaching to the choir, but I did want to mention it and affirm the amazing work so many folks here have done. As outsiders to the world of specifications, this work all gets a huge thumbs up from us. Our second takeaway is probably what you started thinking a couple minutes into this presentation. Building MoxPop was a lot more work than not building it. While it's been useful, I wouldn't say it's been essential for us at WebhookDB, at least not yet. We do expect this to change as it's developed further, and we get to lean on it for more and more new integrations. We may have been able to solve some of our problems with other tools or with a little manual labor. However, and this is a big however, the third takeaway is whether or not it was worth it, building MoxPop was a whole lot of fun. Software development at scale is frustrating and stressful. I don't have to tell all of you. And two of the best ways we have found to make it more fun are to build better automated testing and tooling, and to work on tightly scoped projects that allow us to be creative within that scope. In the case of MoxPop, when your project is a tightly scoped testing tool, that's the best of all worlds. MoxPop helped fill out integration testing around WebhookDB, and it was a ton of fun to work on. This is largely because AsyncAPI is so well done, from the spec to the tooling to the documentation and the community. I really can't say enough good things.
Thanks so much for watching us today. You can go check out Mox Populi on GitHub. It's a Go project you can use as a CLI or a library, but even better, there's a link in the README that allows you to try this whole thing out yourself using curl. Really, you should go grab some events from your own services, run them through the endpoint, and see what sort of async API spec you end up with. We hope it's as useful to your teams as it has been to ours. You can also reach Rob and me via email if you want to follow up. We're happy to answer any questions or just talk shop. Finally, if you're dealing with any third-party API integrations, you should check out WebhookDB. And if you're ever in Portland, Oregon, please let us know. We'd love to buy you a coffee and tea or just chat. Thanks again to AsyncAPI Conf. This has been great.